So good afternoon, class. Welcome back to Mass 802, Algebraic Topology. So last time we are looking at path and path homotopy. So you can recall the definition of a path. We define a path to be a continuous mapping from from the closed bounded interval 0 to 1 into X, where X is a topological space. Any such continuous mapping is called a path. And then we define path homotopy. So if you have two paths, F and G, from a point x0 to a point x1, so you define a homotopy of path relative to their endpoint. So therefore, they must share the endpoint. The initial point of the path and the terminal point of the path must be the same. So if you have such path, we normally draw arrows to show the direction so that we identify initial and terminal. So any homotopy that is relative to the endpoint is said to be a path homotopy from F to G. You remember what we call homotopy? It's a continuous family of continuous mappings. And the mappings should be from where to where. So this time around should be a continuous family of paths. So these maps, they should be from the closed bounded interval into X. So it's just like a family of paths that transform this path F into G over a time interval of 1. And then throughout the homotopy, the point x1 and x0 are fixed. That is what we mean by relative to the endpoint. So we say the relation of path homotopy. I think that is the last thing we look at in the class, that the relation of path homotopy, that is, we say F is related to G if and only if F is homotopic as a path, is path homotopic to G. So, which means there is a homotopy from F to G. This relation of path homotopy is an equivalence relation. We proved this in the last class as a theorem. We labeled as theorem 2.3. So we had that actually. So from that point, we are still talking about path. We have an equivalence relation. And what is the use of having an equivalence relation on the set? So if you are talking about a set of all paths sharing the same ends, and you talk about having an equivalence relation, this equivalence relation will partition this collection of all paths into what? Equivalent classes. Okay? So you imagine you have a fixed initial point and a fixed terminal point, and then you think of all paths from this to that in a particular space. Then you say that path will be homotopy to this if you have a path G and path F, but there may be some other path H which is not homotopy to G, and so on and so on. So if you take the collection of all paths from this point to that point, the relation of the path being homotopic is an equivalence relation, so it will partition the set into equivalent classes. And then you can now think of having equivalent classes of the path. So paths that are homotopic, we think of them as one, as the same path. So if you can deform one path into another, that is to take the shape of another path, then we see them as one and the same. For example, if you are talking about path, starting from one point x0 and ending at that x0, this path F, I can shrink down this path to a point. So it is homotopic to the constant path. So all such paths that can be shrunk down to this point will be in the same equivalent class and they will be considered as the constant path. I hope it's okay. So we denote the equivalent class, we denote the equivalent class equivalence class of path, well, of F. So F being our path under path homotopy. By F, like this. So this will be the equivalent class of F. That is the set of all paths that are homotopic to F. So this will be our notation for the equivalent classes. But actually, we are not going to be interested too much on paths from one point to another point. We will be interested mostly on paths that have the same initial and the same terminal point. I mean, the initial and the terminal point are the same point, which means loop, So those are the ones that we'll be interested in. What is our target? What we are trying to do is to actually gather together all these collections of the homotopy classes and define a group structure on them so that we develop a group on the topological space using this path. I hope it's okay. But then we'll be using loops. So we require a binary operation, a way of combining paths. And you can be able to do that if the path share point. So we define product of paths. So given two paths, F and G, so in a topological space X, such that F of 1 is equal to G of 0. So meaning the terminal point of F is equal to what? The initial point of G. So this is the path F, and that is the path G. So this is F, and that is what? G. So F start from this point x1, x0 to x1, and G start from x1 to x2. So if you have path like this, then you can take the product of the two paths. And the product should be a path in the space. So we define product of F and G which we denote by F dot G. So you cannot define product of two paths unless this condition is what? Satisfied. So this is a crucial requirement for the definition of what? Product of paths. So you have to see that the terminal point of one path of the first path is the initial point of the second path. Okay? So you can see that if x0 is not equal to x2, you cannot think of defining G times F. That will not be defined. Okay? So product is defined only when this happens. Okay? And in that situation, the product is defined by concatenation. By concatenation as Fg of S to be equal to F of 2S and G of 2S minus 1. And this is in the situation where S is from between 0 and a half, and here S is from between half and 1. So actually the product is also a function from the interval I into the space. because these values are inside the space, since my f and g are mapped from I to the space. So the domain of the definition is the interval I, and then the codomain is x. But why is this a path? We have to check that it is a continuous mapping. Yeah, first of all, it is defined. Well, you can see that it is well defined because if you check here, you see that at s equal to half, you have f of 1. And you have also here g of 0. But then f of 1 equal to g of 0. That is why this condition is very crucial. I hope it's okay. So that's why it is required that this equality must hold. So since f of 1 is equal to f of 0, this mapping is well defined. Is it continuous? Yeah, it's continuous by pestle lemma. You remember it? Do you remember pestle lemma? Okay. If you define a function, piecewise on two separate subsets of the domain, where the piecewise definition coincide at the intersection of the separate subsets, then that function will be continuous. So this is the pestle lemma. So by pestle lemma, this function is continuous, and so it is a path. It is a path in X. So this is, we have gotten a new path. Can you see it in the picture? The new path is this one. Let me draw it in red. So you can see the path. Well, f is starting from this point, and then in one time interval, like 1 hour, in an hour, you arrive at this. And then g, in another 1 hour, you arrive at this. But f times g will follow through f, but you double the speed. So therefore, in half an hour, you arrive at x1. And then the next 1 hour, you arrive at x2. So actually, the red is your product. And the domain is still 0 to 1. Is that okay? All right. Yeah.
Is it possible to define the product of three parts in this manner?
Yeah, if you still have another path extending from x2 to x3, then you can still define g with h. If this is h, then g times h is still defined. So you can continue like that. You can have a whole sequence of path, successively sharing the terminal point is equal to the initial point. So long as the terminal point is equal to the initial point, you can always have a product. So you can do it like that. But this time around, if you want to define f, so f times g times what? H. So this one should be defined, you divide the interval into 3. So the 1 hour time interval, you divide into 3. Are you following? 1/3 of the time, and then the next second 1/3, and then the last 1/3. You can do it that way. Okay? In fact, we will have to, yeah. How do you know that F of 1 is well, no, it's a condition. It's a restriction to definition. It's a condition. You have to check. We are not saying we know. Before you define the product, you have to check that this is satisfied. So you can have a path and another path, and you think of multiplying them together. Okay, it has to be one path like this, and then the next path should start from that last endpoint of the first one and extend to somewhere else. Are you following? So we are saying that before you think of multiplying, you have to check that this condition is holding. Otherwise, product of path is not defined. From where? Yeah, to check, that means look at f. This is the terminal point. And look at what I call G. This is the initial point.
This f of s and g of 2s, minus 2s minus 1.
Yeah, f of 2s. If you substitute s equal to half, you have f of 1 here. And again, if you put s equal to half, g of 2 times half minus 1 is g of 0. But then the condition said they are equal. So this is what I mean. So those are equal at the boundary here. And so therefore the function is well defined. So this is what we mean by product of paths. So my next result is going to say that path homotopy respect this product of path. That is, product of path is preserved by path homotopy. Okay? So, lemma 2 point, this should be 2.4, okay? So if f, did you understand this now? So I'm talking about f is a path, and f1 and f0 and f1 are path, and g0 and g1 are also path. But what is this notation now? I don't know whether I have introduced it. So what is that notation? I'm saying that f0 is path homotopic to f1, and g0 is path homotopic to g1 in a space x. This space is a topological space now. Is that okay? And when you say path homotopy, such with f0 of 1 equal to, so let me say g0 of 0, and f1 of 1 is equal to g1 of 0. So meaning the product f0 times g0 is defined, and the product f1 with g1 is also defined. So if that is the case, then I can multiply f0 with what? g0, and I can also, this path f1 with g1, these two paths also exist. Okay, the path here exists. But the theorem is that these two paths, if this is path homotopic to that, and this is also path homotopic to this one will also be path homotopic. Did you get it? Yes. So it's not actually difficult to see, because it's like you are having this path f0, and then you have this one g0, but then not g0 here, f1, and there is a homotopy from f0 to f1. So think of having a homotopy, so which means I have a whole continuous family of paths, that transform this f0 to f1. And then you have also g0 and to g1. Again, there is a homotopy. That's what we mean by. So f1 is homotopic to f0, and g0 is homotopic to g1. But then f0 share the same endpoint. I mean, the product f0 times g0 is defined, and the product f1 times g1 is also defined. So if that is the case, the product will also be this product of this part at the top here, f0 times this g0, will be homotopic to f1 g1. I don't know whether even it is even clear to you that, because of the fact that there is homotopy, this condition here is redundant. Even without having to state it, because of the fact that there is homotopy, from here down there. Okay? You can see that once F1, G0, F1 is equal to G0 of 0, then automatically this will also happen. Did you see that? Because G0 of 0 is equal to G1 of 0. And F1 of 1 must be equal to F0 of 1. Yeah, because of the fact that there is homotopy here. So this condition will suffice, the first condition here. But then there is nothing wrong in putting the other condition, just for emphasis. Is this okay? So how do we prove this thing now? What do we have? What we have is there is a homotopy here and there is a homotopy here. And then this condition. So this is what we have. So we take a homotopy. So let Ft be a homotopy, path homotopy. From where? F0 to F1. And then you take the other homotopy also, G0, GT. But I don't know whether you notice I did not write T coming from, well, so many times I will just be writing FT without having to write thinking of it as the family without having to write the index set. Index set is always where T is ranging, is always what? I, the interval is 0, 1. So, and GT, T in what? I. Be a path homotopy also. From G0 to G1. Okay? So if you have this path homotopies, then the product, actually for each T in I, the product F, I don't know that I can F T G T is well defined. Why is it well defined? Since Ft of 1 is always equal to that F0 of 1. And also G T of 0 is always equal to G0 of 0. So since these are the same, those are also the same. I hope it's okay. So this is always happening for every T. So it means, so actually the homotopy is relative to this point. So this point are always fixed. So therefore, we always have, if you take Ft here, it shares the same terminal point as the GT over here. So you see that the product is always defined corresponding to every T. So you have a flow of maps. I hope it's okay, over time. And that already defines what? A homotopy from the product F0, G0 to F1, G1. It's already a homotopy. It's continuous, it's well defined and continuous. That product, and continuous by Pestel lemma. Okay? All right. And by pestle lemma, maybe it is what? Continuous. So you have a continuous family of maps from F0 to, so it will not be difficult to show. I don't know that I can leave it at that level. I just say it will not be difficult. Oh, okay. It is then easy to see that this continuous family of maps is a homotopy. Ft0, Gt, T in the index set is a homotopy. From where? And homotopy here, I'm saying path homotopy. Well, many a times I'll be missing the word path to mean path homotopy. Okay? From where? F0.G0 to F1.G1. Is this okay? What do you mean by is a path homotopy? It means if we evaluate this thing at 0, we should get what? That is at t equal to 0. F0.G0 should be equal to, but that is it. That is exactly what it is. And the F1G1 should be that one, which is exactly what it is. So there is no trouble seeing that it is actually a path homotopy. In fact, there is almost nothing to write down. So, I can put the small square. Okay? What is the meaning of that small square? End of proof. QED. What is QED? That is what it means. Yes, he said quite easily done. Modern mathematicians formulated that. But then it actually means quod erat demonstrandum. And that's what it means. It means this is what needs to be proved. Or this is what needs to be demonstrated. So that is full stop. That is what needs to be demonstrated. That's the meaning of that small square. You always see me writing a small square at the end of proof. If you are reading mathematics textbook or papers, at the end of every proof of a lemma or a theorem or proposition, you always see this small square. That is what it means. Okay, QED, quod erat demonstrandum. This is what needs to be demonstrated. But then modern mathematicians will say quite easily done. Is it quite easily done? Most of the time, it's after a lot of effort. It's not that easy. All right. So we have now found a way of multiplying paths together to produce another path. So if you have a path like this, and from the terminal point of this path, another path starts, you can combine the two paths together and have a new path. So you just run over the two paths with a double speed, okay, to arrive there. So with this, I can start talking about fundamental groups. So I can, no. So what I have said so far about path and homotopy and path homotopy, I think that is the second part of the course. Okay, so this will be the third part of the course, the fundamental group. Yeah. So fundamental what? Group. Fundamental group of a topological space. So from now onward, we are going to concentrate on loops. So we are not going to be working with path, but loops. You see, the advantage of working on loops, or let me define loop first. So a path f from I to x, well, so a lot of assumptions already. So I mean, let x be a topological space and f be a continuous mapping from I, to x, where I is the interval 0, 1. So things are already familiar to us. That's why we are allowed to assume certain things. So we skip a lot of assumptions here, okay? Such that f of 0 is equal to f of 1, a point in x. So if it happens that the initial point of a path is equal to the terminal point, the same point, so you have a path like this. This is f of 0. And then it starts from there and again end at that particular point, f. So that path is called a loop. It's not a Newton. It's a loop based at x naught. We need to mention the point because that point is determining the path actually. If you change the base point, it will change. But if the space is connected, you can drag it, you can move it around. We'll see that if you have a path connected space, you can always connect, so no problem. So the advantage of this one, of having considered loops, is that if you have another one, G, then f of 1 is always equal to G of 0. So if you are talking about all loops based at the same point, x naught, they are always composable. You can always multiply them. Product is always defined. So you don't have to worry about that condition because you are dealing with loops. So always the initial point coincide of the second one coincide with what? The terminal point, because in fact everything is the same. Even if you have a third one called H, you can always multiply them all together. I can do G times H times F. I can do F times G times H. You can, yeah, well, we'll prove that is associative, but this is not associativity. What I've written here is not associative. I'm just trying to point out to you that you can multiply anyhow. It doesn't matter which one is the first factor or which one is the second factor. Are you following? But if you have a path F and you have a path G to this point and you have H, only F times G times H is defined. The other one, if you do G times F times H, this is not defined. Are you following? But if you are dealing with loops, everything is defined. Product you can combine anyhow. I hope it's okay. So that's the advantage of working with loops on spaces. Okay? All right. So that is what a loop is. Okay then. So if we restrict our attention, let me write. If we restrict attention to loops in a space based at a point x naught, Then we then denote by the set of, so when you are talking about loops based at this point, then you can now think of equivalent classes of all loops, because the relation of homotopy, so this loop is homotopy to the other loop. You know, if you are looking at these ones in this space, all of them are homotopic, because I can shrink each one of them to a point. So they are homotopic to each other. I hope it's okay. So, but it's not necessary that all loops are homotopic to each other, because you can think of being on or let me think of being on a torus. So if you identify a point here, x naught, then I can have a loop like this, f, and then you can have a loop like this, g. But then f and g are not homotopic, because there is no homotopy from f to g. You cannot deform or shrink down f to g. This one goes around and this one goes the other way around. I hope it's okay. So, but if I draw a loop like this and another one like this, the two are homotopic. Both of them can be shrink down to a point. So not every loop you can shrink down to a point on this space. Some of them, if you try to like F here, they'll get caught around the surface of this thing, like G also. So you can think of homotopy. So loops are either homotopic or not. So you can think of homotopy classes of all loops, because the relation of these loops being homotopic is also an equivalence relation there. It's almost the same proof as what we have done for loops for homotopy of path. I hope it's okay. So this loop and that loop will be in the same homotopy class, because they are homotopic, and they will be in the class of constant loop. There is a constant loop, the one that stay there, the mapping, the constant mapping that maps the entire interval to the point x naught. It's also a path. It's a continuous mapping. I hope it's okay. So you can think of homotopy classes of loop, equivalent classes of loops. So like here I'm seeing about 3 classes, because there is a constant loop and all these ones are also homotopic to it. And then this loop f, there will be so many ones that are homotopic to it. Okay, and g. So I can see about 3. There are even more. Actually, there are more. Okay. For example, if you do a loop like this, it goes round and come out and go round again. Maybe it goes round 3 times and come back to x naught. That loop is not the same thing as f, because it winds round the torus 3 times. So, and f wind round only once. So it's not the same thing as f. So there will be so many homotopy classes of loops based at the same point. So you can now see that, so we can, if we restrict attention to loops based at x naught, we have so many homotopy classes, and then the collection of all homotopy classes. So the class or the set we denote by phi 1 x naught. So this notation has to mention the space and the base point. Okay, because if I change the base point, it's a different thing. I'm talking about different loops. Okay, so and the base point. So the set of all loops based at what? At x naught. But is it a set? It's a set. That is the equivalent classes. That is the collection of all equivalent classes is a set. How do you know it is a set? How do you know it is a set? If you take the collection of all equivalent classes of an equivalence relation, defined on a set. Is it a set? Huh? Collection of the equivalent class. That is the class, the partitioning of the set. Is it a set? How? How do you know it is a set? This is the question I ask. Okay. It's all right. So is that set is donated by this. Okay? So which means it will be the set of all x naught. So homotopy classes of all those loops such that f is a loop in x based at x naught. Okay, so you take the equivalent classes. So members of this set are equivalent classes. In fact, it is this set that will be our candidate for the group. So we have just defined addition or multiplication of what? Path. So we extend that multiplication to homotopy classes so that we have a group structure on this. So this collection will be a group, and that will be the fundamental group of the space, based at x naught. So we prove the fact that it is a group. Now this will be 3.1 then. So the set phi 1 x x naught, and then we have introduced that is a group with respect to, when you call something a group, you have to mention the binary operation with respect to which it is a group. With respect to product of, so you cannot say product of path or loops. Loops are always multiply, you can multiply them always. But you can't say product of path because elements are not path there. So it has to be product of homotopy classes of loops. Okay? Product of what? Of loops in here. Defined by, so if you take a homotopy class of loops, based at x naught, and another homotopy class, so the product should be, naturally it should be the equivalent class of the product of f and g. That is always defined because this is a loop based at a point. So what happens is you have a loop f and you have another loop g based at x naught. The product of f and g is this loop. In the half of the time it goes around the h, the f, and again at the next half it comes. So it's a loop. You see, don't think, you see, when you are talking about loop, it can go and come back to the point and still go around and come back to the point. So long as where it started ended there, then it is a loop. Are you following? So that is it. So this is a loop still, the product. So that loop, so think of the equivalent class of this one, multiplied by equivalent class of this, will be the equivalence class of their product. So this is how you define it. Okay? So we have to prove that this thing is a group. So how do you do it? To prove that it is a group, you have to show that, first of all, you are defining something in terms of equivalent classes. So you have to show that it is well defined. Well definedness means what? You see, this class, this is a set of elements, and you pick one element from the class. It's called the class rep. What if you change the class rep? What I'm saying is what happen if this class is the same thing as the class of F1, and this class is also the same thing as the class of G1. So, which means this product and this should be the same thing. Because if this product and this are not the same, then we have a problem. Since this is the same class, this is the same class, this is the same class, so that pair is one element, and this is one element. So the resulting product here, if you multiply, it should be F1 times G1. It must be equal to this one. Because if it is not equal, you are saying one element is mapped to two different images under this binary operation. That is a problem. So that is why you must have equality to happen here. That is well-definedness. Are you following? But did you remember our lemma? The lemma say if F0 is homotopic to F1 and G0 is homotopic to G1, then F0 composite G0 will be homotopic to G1 composite F1 G1. Are you following? That means these classes are the same. So if these are the same, this will be the same. So the lemma 1.02, 2.4, the lemma 1.4 we prove has already shown that lemma has already shown that what this thing is well defined. Okay. So first of all, this is always defined. Actually, if you remove the F naught. So first of all, this is well defined because you are dealing with what? Loops based on X naught. So since F and G are loops based at the same point X naught, the product is always the product, which one? F composite G is always well defined. It's always defined, it's always defined. And by the lemma, you remember that lemma 2.4? Do you remember it? And by our lemma 2.4, the product of path homotopy is well defined. So that lemma has already done the job for us. Okay? So what remains is to verify the three axioms. It remains to verify the three axioms of a group. So we have a well-defined binary operation. Then we have to show that, you see, well-definedness, this is already closure. Since it is a binary operation, it's closed. So which three axioms do we need to show? That the operation is associative.
In the sense of inverses are identity elements.
That there is an identity element, and every element has an inverse. But then in group theory, we know the inverses must be unique. So if we just produce the inverse, it is unique. Okay? All right. So how do you do that? Let's start with associativity. Okay? So if F, G, and H are paths, not loops. In fact, I want to show associativity generally for path. Sharing the terminal equal to the initial. So I just want to, if you can do it with that, that is, if you can take three paths, F, G, and H. So G and H, so that F1 is equal to G0 and G1 equal to H1, and show associativity hold. And it also holds for the loop situation, because the loop situation, the product is always defined. Okay? So we'll show that associativity hold for any configuration of path like this, generally, not necessarily looking at the loops. Okay? So if these are three paths in the space X, such that, well, what I mentioned here, F1 equal to G0 and G1 is equal to what? H0, meaning the product is defined. Okay? Then so both F composite G, this is defined. Composite H and the other one, F composite G. But is it right to be saying composite? Concatenation. This is a concatenation. We are not composing actually. This definition is not composition of mappings. They are mappings, but we are not composing. In fact, for you to compose, you have to see that the codomain is equal to the domain. But this is not the situation here. So the composition may not even be defined for this case. Okay, so you have to be careful about the terminology you are doing. You see, so I was carelessly saying compose. No, but it's not composition. It should be what? Dot product. You can say dot. We understood what you mean. Concatenated. It's a concatenation actually. Okay. So these products are always defined. Yeah. Do you understand what I mean by I define here? Yeah, because once they share this point, the product is defined. And if they share at this point, the product is defined. So I can always do this product. And what is the terminal point of this product? It is the terminal point. It is the terminal point of G. The terminal point of this product is the terminal point of G. So this dot is defined. Because if you want to do this product, you have to compare the terminal point of F with the initial point of G. And then after getting the resulting product, so it is the terminal point of this resulting product with that you compare with the initial point of H. But since this terminal point is equal to the terminal point of G, and by the given hypothesis here, assumption here, that is equal to that. So this is defined. And the same situation also here. So these products are defined. Okay? So what remains is to show that this is equal to that. It's equality now that we want to establish. Okay? All right. So we define a map. I can take a shortcut and say a continuous map. And then we can justify why it is continuous. In fact, we have made a remark that whenever we say continuous, whenever we say a mapping here, we mean continuous mapping. But then I think I need to emphasize it here, a continuous map. Phi from I to I by, so this mapping is defined to be this. So S over 2 for S from 0 to a half. It should be S minus 1 over 4 for F's from a half to 3 by 4. And then, so 2S minus 1, 3 by 4 to 1. Okay. From where do we get this? I don't know. From what? So what are we trying to do? Actually, what I'm trying to do is to use a lemma from one of our previous discussions that I don't know that lemma, I can remember the label. There was a lemma we proved. We said if you have a function, continuous map, phi, I'm sure you can remember that. If you have a continuous function or a path from in a space X, and you have a continuous map from I to I satisfying phi of 0 is equal to 0 and phi of 1 is equal to 1. So 0 is mapped to 0 and 1 is mapped to 1. Then this composite will be, so F after phi is a reparameterization of F and will be homotopic to F. I don't know that I proved this. I'm sure we proved it in one of the previous discussions. Okay? So the same thing I want to do here, if I can show that this is a reparameterization of that, then I think the proof is over, because we will just invoke that lemma. Yeah. So if you are dealing with two paths, that is lemma 2.2. Okay. So if we are dealing with two paths and you want to show that they are homotopic, path homotopic, just establish the fact that one is a reparameterization of the other. So, and how do you get one to be a reparameterization of the other? Define that mapping F from I to I satisfying this condition and show that the composition of F with this mapping is equal to your other. So if I can define this map and show that if I compose this with phi, I get what? This particular composite here, which is a path. Then it means this path is a reparameterization of this. And so therefore they are homotopic, path homotopic. So this is what we are going to do. So I'm trying to construct that map. Okay? So how do you construct it? So we want to see that so the way we did it is actually, in fact, with this map, if you check this, you see that then F H composed with phi will be equal to F dot G dot H. If you do this composition, you arrive at this. So it's just a matter of applying the meaning of this. What does this mean? And what does the composition mean? Are you following? So you see, you start by applying the composition, and then you apply this dot, and you arrive at that. So how do you get this mapping? You divide so it's a map from where? From I to I. So think of it like this. So we had, so this is how we constructed that mapping. So we think of a square. This is I, and that is I. And then this is 0, that is a half. This is what? 1. It's a half, and that is 1. Okay? So this is 1 already. So we think of dividing this region into 3. So first half. In the first half, and then the next is 3 by 4. Okay? So this is 3 what? 3 by 4. So this is what you have. So you have a linear graph, you know, that is the slope is half. Cool? In fact, it's not like this. Actually, in the vertical axis, because you divide by 2, so it should be 1 over 4. Since half will be mapping to 1 over 4. Are you following? So it's like this. So it's a straight line like this. That is the mapping phi, the graph. And then straight line like this, and another straight line up 1. Yeah, the slope is clear now. In the second part, the slope is 1. In the last part, the slope is 2. Okay? But then the intercept at y-axis. It's okay, ba? Is it okay? It's okay, ko? Yeah. So that is how I arrive at this formula. So how do you do it? You look at this. This point is 0, 0, and this point it was a half and 1 over 4. So you can get the equation of a line given 2 points. A straight line between 2 points. So if you do that, this is the equation of the line. Okay? And the equation of this line also. So, and the equation of that line. That is it. Okay? And it's easy to calculate. You can easily calculate this one. Do this composite and see that it is equal to this. Which means this composite here is a reparameterization of this composite. Okay? So that's what we are having. So, where's my, can clean it. So thus, F composite, dot G dot H is a reparameterization of F dot G dot H. And so by the lemma what? 2.2 in our notes. The two are path homotopic. So F dot G dot H will be path homotopic to, is path homotopic to F dot G dot H. So we have the two to be path homotopic. This is how we prove that it's isomorphic. The two are path homotopic. So that means associativity. Okay? But if we now restrict attention to loops based at a point, this is always defined, and that is always defined, and then they are homotopic, because it's part of the general thing we observe here. Okay? So, it means by restricting attention now, if we restrict to loops based at what? At x naught. We have that combined with the lemma. So we have that if these things are homotopic, then they have the same homotopy classes. Oh? They have the same homotopy classes. So which means product of homotopy classes is associative, or it extends there. Product of homotopy, path homotopy classes. In what? Phi 1 x x naught. It's associative. Okay, next is we prove that there's identity element. Okay, we still have time, or we can stop here. All right, so maybe we stop at this point. In the next class, we will continue the proof of this lemma, or this particular theorem. So it remains to show that there's identity, and this identity will actually be the path that will remain there. It will be, so you see, if you start from x naught and f, so the constant path, you just do constant path. Constant path means you should stay there. You stay there for 1 hour, and that is all. It means everything is mapped to x naught. So if you donate by c x naught, the constant path that stays there, then this will actually be homotopic to f, and f dot c x naught will still be homotopic to f. That will be our candidate. The constant path at that particular point will be our candidate for what? For the identity. And you can reverse path. Yeah, f like this. Then I can go in the reverse order. Go back. F inverse. But then we donate by f bar. And you see that if you go f and come back, there will be a homotopy between this f and the composite f bar to the identity at x naught, so that f bar will actually be the yeah. How do you define f bar? F bar will be of s will be equal to f of 1 minus s. Okay, so that at 1 it is 0, and there at 0 is already 1, so you are coming backward. So this is, we are going to prove this, and then once we prove this, we have a group. That group pi 1 x of x naught will be the fundamental group of the space, of the topological space x based at x naught. So we have a group. This is the one called fundamental group. Thank you very much for your attention. I will see you in the next class.